Our prior two lessons, we've been working on factoring polynomial expressions. And as we've been doing this, trying to get the basic parts, we've been asking ourselves with our polynomials, does it have a greatest common factor? So if we're working with x to the third minus 3x squared plus 2x, we're looking to see, is there something that each of the terms have in common that we can divide out? In this case, they have an x. So we can divide out an x, and we'd be left with x times x squared minus 3x plus 2. Well, as we were doing in our last lesson, we're looking at polynomials like we see on the inside, asking you if we could factor those. Typically, we've been having polynomials with 4 terms, and here we have 3. So the question is, can we write this expression as 4 terms? So if we think about where those things came from, when we had them as 4 terms and we looked at it factoring by grouping, it was 2 binomials being multiplied together that made those 4 terms. And the 2 middle terms ended up condensing because they were alike, so then we had 3. So if we could backtrack one step to figure out, well, what were those 2 like terms that we added, then we would have the 4 needed, and perhaps we could factor by grouping before. So when we're thinking about this, we want to think about it in terms of 4 terms. Remember, in order to get these, we were distributing. So we're going to use what we have here for our polynomial and take the leading coefficient, which was a, times the constant, which is c. So we're taking 1 times 2. So we're going to think, what times what gives us 2? And then again, these middle terms here, we're trying to see what we can add together to make that. And so we're going to think, what plus what gives you negative 3? So it has to work for both rules. So what are we multiplying to get 2 and adding to get negative 3? I could use a negative 2 and a negative 1 to make both of those rules true. Negative times a negative is a positive, and a negative plus a negative is a negative. So I'm going to rewrite this polynomial using these two to represent my linear term, that negative 3. So I'll have, inside my parentheses, x squared minus 2x minus 1x plus 2. Since we have expanded that linear term using these two, we now have 4 that we can look at perhaps in factoring it into pairs. So again, I'm going to look at the first pair and see what they have in common. Well, x squared and 2x, they have an x in common, so I could divide that out. Now I have x minus 2. My second pair, I could divide a negative 1 from each, so I'd have negative 1 times x minus 2. And again, what we were talking about before with our 4 terms of factoring, we want to see them being multiplied by the same amount. Here we can see that x minus 2 is being multiplied by x and negative 1. So as we write this in factored form, we would have x, the greatest common factor, times x minus 2 times x minus 1. And again, to check the equality from what we started with, we would take our 2 factors here, multiply them together, combine your like terms, distribute through the x, we should get back the original expression. Let's take a look at another one. Here we want to factor x squared minus 11x minus 60. And again, the first question we want to ask ourselves is there a greatest common factor? So as we look at each of those terms, we want to see if there's something alike we can divide out. And in this case, there is not. So since there isn't a greatest common factor, can we do like what we did in the last problem? Can we rewrite this expression so it has 4 terms as opposed to the 3? So in order to do that, again, we think about the leading coefficient, a, which is 1, times the constant c, which is negative 60. So we're going to think, what times what gives us that product, negative 60? And what plus what will add to give us this coefficient for the linear term, negative 11? So you can use your multiplication table if you like to see where 60 shows up, and then look up and to the left to see what numbers you can multiply together to get that negative 60, but add to get the negative 11. Well, I know that 4 and 15 will make a 60, and if I need it to be negative, what if I made the negative at the 15 negative? 4 times negative 15 is negative 60. 4 plus negative 15 is negative 11. It works for both requirements. So we're going to rewrite this linear term using these two to represent it. So we'll have x squared minus 15x plus 4x minus 60. We have the 4 terms that we needed, so again we will look at it in groups and see what we can divide out. So this first pair, x squared minus 15x, has an x in common. So if I divide that out, that would be x times x minus 15. The second pair, we want to see what we can divide out from there, and I can divide out a 4 from each, so I'd have 4 times x minus 15. So again, we want to see them being multiplied by the same amount. So they have a greatest common factor of x minus 15, which is being multiplied by x plus 4. Therefore, our factors are going to be x minus 15 times x plus 4. Again, to make sure that we've maintained the equality, if we take x minus 15 times x minus 4, we'll get back our x squared minus 11x minus 60. Here's a third polynomial, 3x squared minus 12x minus 180. Again, the first question we want to ask ourselves is, does a greatest common factor exist? So again, scanning each term of the polynomial, hopefully we recognize that there is a 3 that we can divide out from each term. In doing so, we'd have x squared minus 4x minus 60 to work with. At this point, again, you want to ask yourself, can we write this expression as 4 terms? In order to do that, we're going to take the leading coefficient times the constant and think, what times what gives us negative 60, and what plus what gives us negative 4. So again, you could look at the multiplication table, find where you get 60, look up and to the left to see what factors would help you make that happen for both rules. I know 6 and 10 will give me 60, and if I have 6 and 10 and make the 10 negative, that will also add to give me the negative 4. So if I use the negative 10 and the positive 6, it's meeting both the requirements. Therefore, I can write my polynomial with 4 terms, x squared plus 6x minus 10x minus 60. Again, the goal with the 4 terms is, can we look at it in groups and divide out anything that they have in common? So the first pair, we can see they have an x in common, so we'll divide out the x, so we'll have x times x plus 6. The second pair, we can see they have a negative 10 in common, so I'll divide out the negative 10, I would have x plus 6. And again, we want to see, are they being multiplied by the same amount? They have that common factor of x plus 6. So we could write this as 3 times x plus 6 times x minus 10. Again, to check the equality that we have from the beginning, I would multiply these two factors together, combine the like terms, distribute the 3, and we should end up with 3x squared minus 12x minus 180. Let's take a look at another one. Here we have negative 2x to the third plus 16x squared minus 32x. Again, with your polynomials, the first question you ask yourself is there a greatest common factor? So looking at each of the terms, we can see that they have an x in common. Also, they have a factor of 2. We usually don't like having leading coefficients being negative, so why don't we divide out a negative 2x from each term? In doing so, we would have x squared minus 8x plus 16. Again, at this point, we want to see if we can write the expression as 4 terms. So we're going to look here at the inside of the parentheses and use the leading coefficient times the constant and think, what times what will give us 16, and what plus what will give us negative 8? Well, we know that 4 and 4 will multiply to get 16, and 4 and 4 can give us 8. If I make both of the 4's negative, that would meet both of the requirements. So I would have negative 4 times negative 4 giving you the positive 16, negative 4 and the positive 4 giving us the negative 8. So again, we're trying to rewrite this with our 4 terms. So we would have x squared minus 4x plus 16. We like having the 4 terms because we can look at them into pairs and see what we could divide out. So the first pair, we can see we could divide out an x. So we'd have x times x minus 4. Second pair, we could divide out a negative 4, so we'd have negative 4 times x minus 4. Again, we want to see, are they being multiplied by the same amount? So do they have that common factor? We do, of the x minus 4. So we have the greatest common factor of negative 2x being multiplied by x minus 4 times x minus 4. Well, notice x minus 4 is being used twice. So in mathematics, we like to fully simplify our results, and to show that something is being multiplied by itself, oftentimes we use the exponent to represent it. So we could write this as negative 2x times the quantity x minus 4 squared. Again, to check the equality, we can distribute the two factors. So you multiply your x minus 4 times x minus 4, combine your like terms, and distribute the third factor, negative 2x, through, and you should get back your original expression. Negative 2x to the third plus 16x squared minus 32x. Let's take a look at another. X squared minus 16x plus 64. We want to factor it completely. The first question you should ask yourself is, does it have a greatest common factor? And looking at each of the terms, the only factor they have is 1, so that's not going to impact our results. So the next thing you want to ask yourself is, can we write the expression as 4 terms? So again, at this point, we're thinking about that leading coefficient and the constant. So what times what can give us 64, and what plus what will give us a negative 16. Thinking of the factors of 64, I can use an 8 and an 8. And if both of those 8s are negative, they'll add to give me the negative 16 that I need. And also, if they're both negative, they'll multiply to give me the positive 64. Therefore, I can rewrite this as the 4 terms, x squared minus 8x plus 64. We like having the 4 terms because we can split them into pairs and see what we can divide out from each. Our first pair, we can divide out an x. Our second pair, we could divide out a negative 8. Therefore, we would be left with x times x minus 8 and negative 8 times x minus 8. Again, at this point, we're looking to see, are they being multiplied by the same amount? They are, so we have x minus 8 being multiplied by x minus 8. Again, notice that these two factors are the same, so we can condense it even more by simplifying it to x minus 8 squared. This is what we know as a perfect square binomial. When we multiply it out, we result in a perfect square trinomial. Let's try this one. 6x to the third plus 66x squared plus 144x. Again, we're looking to see, does it have a greatest common factor? I can see that each term has an x we can divide out, and also each term is divisible by 6. So the greatest common factor would be 6x. Again, we want to look inside the parentheses and ask ourselves, can we write the expression as 4 terms? So we're going to think of the leading coefficient and the constant. So what times what gives us 24? And then what plus what gives you that linear coefficient of 11? Well, I know 24 comes from 8 and 3, and that also gives me an 11. So if I use a positive 8 and a positive 3, that's meeting both requirements. So we'll rewrite the polynomial with the 4 terms. Again, we like having the 4 terms because we can split them into pairs and divide out what they have in common. The first pair has an x in common, so I could rewrite that as x times x plus 8. The second pair has a 3 in common, so I could write that as 3 times x plus 8. Therefore, we're checking again, are they being multiplied by the same amount? They have that common factor of x plus 8, so we could rewrite this as 6x times x plus 8 times x plus 3. As always, you can check the equality by distributing these two factors, combining the like terms, then distributing through the 6x, and that should bring you back to the original polynomial that you started with. Let's try this polynomial, x squared minus 64. Again, the first thing we're looking for is there a greatest common factor? And we can see that 1 does not exist. So again, our goal is to be able to write it in 4 terms. Now maybe you noticed that we had the linear term missing. In the past we said you could always put a 0 for the placeholder of a missing term when you're working with the polynomial. So we have that here, because we're going to use this to help think of our number pattern. Again, leading coefficient times the constant. What times what gives you negative 64, and what plus what gives us 0. So it has to be the same amount that we're multiplying to get the negative 64, but adding them to give us 0. Well, in order to do that, 1 would have to be negative and 1 would have to be positive, and we know 8 and 8 will multiply together to give us 64. So if 1 is negative and 1 is positive, that meets both rules. So we'll rewrite it as x squared minus 8x plus 8x minus 64. Again, we like the 4 terms because we can look at them into pairs and divide out what they have in common. So the first pair has an x that we'll divide out, so we'll have x times x minus 8. The second pair has an 8 we can divide out, so we could have 8 times x minus 8. Again, we look to see, are they being multiplied by the same amount? Yes, it's like they have a common factor. So we can write it as an x plus 8 times an x minus 8. Again, to check the equality, you can distribute the 2 factors, and that would bring you back to the original. This is what we often call a difference of squares, because we notice that it's the same value being used, one of each of the opposite signs, which results in the linear term being 0. How about this polynomial? 5x to the third minus 500x. First thing we should be looking for is there a greatest common factor? And we can see that both terms have a 5 and an x in common, so we'll divide that out. The next question is can we write it as an expression of 4 terms? Well, we can see that we're missing that linear term again like we had before, so if it helps you to write it in, put the 0 for the placeholder. And so we're going to think leading coefficient times the constant. What times what gives us negative 100, and what plus what equals 0. So again, same amount, but 1 will have to have a positive and 1 will have to be a negative. And I know 10 will work for each of those. So using a positive 10 and negative 10, we're going to rewrite that trinomial into 4 terms. We like having 4 terms because we can split them into pairs. And the first pair has an x in common we can divide out. So we'd have x times x plus 10. The second pair has a negative 10 we could divide out. So we have negative 10 times x plus 10. So again, we're looking to see, are they being multiplied by the same amount? And they are. So I can rewrite it as 5x times x plus 10 times x minus 10. Here's our last polynomial, 2x squared minus 24x plus 54. Whenever we're factoring, we always ask ourselves, does it have a greatest common factor? We can see that each is divisible by 2. And again, you want to ask yourselves, well, can we take this trinomial and write it with 4 terms? So take that leading coefficient times the constant. What times what gives us negative 27? What plus what gives us negative 12? I know a 9 and a 3 would make both of those work, and both of them would have to be negative. So I can rewrite it with my 4 terms. X squared minus 9x minus 3x plus 27. Again, we like having 4 terms because we can split them into pairs and see what they have in common to divide out. The first pair has an x in common, so we could rewrite this as x times x minus 9. The second pair had a negative 3 in common, so we could have negative 3 times x minus 9. Again, we're looking to see they being multiplied by the same amount, so they have a common factor of x minus 9. Therefore, we could write the expression as 2 times x minus 9 times x minus 3. And again, whenever you're factoring, to check and make sure you've maintained the equality throughout the process, take 2 of the factors and multiply them together, combine your like terms, distribute through any greatest common factors, and it should always bring you back to the original polynomial that you started with. At this point, you're going to do some practice on your own by completing the Unit 6, Day 7 worksheet.